Today we're going to get into discussing discrete Fourier transforms and concepts like signal aliasing and spectral leakage. So uh, we are now, and you are all now experts in continuous Fourier transforms, specifically when we know the algebraic form of an expression, 10t minus 30 from our last example. So when we know the algebraic form of our expression, we could convert this original signal to our frequency spectrum and f, and we know this is n delta f, this is delta f. We'll see those spikes in the frequency spectrum, and we could also create our Fourier series approximation as well. So you have a kind of a signal that, like last time, you could approximate it with this kind of infinite series of sines and cosines, as we discussed, and as you're all experts on in the last lecture. But as we kind of discussed in the in-person lectures, continuous Fourier transform is actually not usually the common case. I need to switch my red marker. Because typically we're not going to know what our original signal is. We're trying to measure new signals. So we're often going to measure a new signal, and we're going to analyze the properties of the signal because we don't know the functional form of y of t. So really, experimentally, we're going to be designing an experiment apparatus to gather, some value. It could be voltage, current, displacement. Many of the examples that we kind of provided previously in our lecture 6. Either the ECG example. It could be again, pressure from a microphone to kind of look at the vocal cords and the vocal noises. It could be, a voltage from, an amplifier from the, anyways, there's myriads of different examples. But typically, you're going to gather that, those values as a function of time with a data acquisition device, like we do in our lab, and you'll get this kind of series of discrete. So again, discrete Fourier transform, discrete data as a function of time, as you can see below here. So this is typically a graph that you'll either capture or you'll be asked to analyze. So we're going to perform a very similar type of analysis. So we could still extract some useful information from this data set just from looking at this graph. So let's go ahead and figure out, what are we getting here? So it looks like we are counting, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're gathering data points. So we're gathering some number of total data points, capital N. Let me use that. So we are going to gather data points, some capital N. That's the total number of data points. What else do we know about this signal here? Well, whenever you gather data points, and in a DAC especially, you're going to gather data at some specific frequency, or some interval, or some sampling rate. So sampling rate or sampling frequency. Sampling frequency. We'll call that f sub s. This is going to be an important parameter here. So we choose, again, in our lab, 10 samples per second. So 10 samples per second. So what is that? That is our sampling frequency, f sub s. So 10 samples per second, basically at 10 hertz. So if I flip that, if I want to figure out what's the time, what is my delta t between my samples, it's just going to be a tenth of a second. So 1 over 10. Or you'll see that we're going to derive some relationships in a second. So my delta t is basically, again, the time interval between successive samples that I gather. So between 8 and 9, it looks like I get a sample at 8 seconds and I get a sample at 9 seconds. So my delta t here, the t is equal to, oops, my pen is failing here for a second. My delta t is going to be equal to, it's not like writing there, is equal to 1 second. Oh, my pen is really struggling here. Apologies for that. There we go. So my delta t is equal to 1 second. So here my delta t is equal to 1/10 of a second. So you can see there's going to be some relationships that follow. So f of s, we're going to see in just a second. So let's think about this signal here, and let's try to kind of figure out some of these key parameters. So we're capturing a total number of signals n, or total number of data points, excuse me, n. So total number of data points n. We sample at some sampling frequency f sub s, and there's some time interval between our points. And is this signal periodic? Is this signal periodic? Well, no, but over this period, we're going to be sampling, again, we could represent any signal, whether it's periodic or aperiodic, over some period. So there's also going to be some period that we could relate the sample as well. So let's go ahead and do some define some definitions. So we just saw, actually previously, that we can relate our sampling frequency to this delta t. So again, I'm going to star some of these key relationships. So we had our omega equals 2 pi f. We also had in our previous that our delta f, our fundamental frequency, was 1 over our period t. How do we calculate our period t here? Well, let's look back at this previous picture. So 10 samples per second, again, 10 hertz. We said that the delta t is just going to be 1 over 10, so we could see that f sub s is equal to 1 over delta t. Again, number of samples per second. So that is our f sub s. How do I figure out what's the period here? How can I write a period in terms of n and double n, the number of my total data points, and my delta t? Well, the period is just going to be, as you can see on the next page here, the period is going to be my total number of points times my delta t. That's going to give me the period of my signal, and over which it repeats. That's another critical expression. But you can see we can now get different expressions and start to plug in. So we already have an expression, f of s is equal to 1 over delta t. So I could plug in and say my period is going to be a function of n divided by f of s as well, as you can see here. So there's going to be multiple relationships, multiple kind of values, and again, you can kind of double check this, and your intuition should match. So in the previous, we had n is equal to, in this example, we had n is equal to 10 points. So n equals 10. Our delta t is equal to 1 second, and our f sub s then is equal to 1 hertz, and everything should match. So everything, but look at all the things. Again, we pulled out the period, we pulled out our total number of points, our sampling frequency, and our delta t just from looking at this curve. So this is an unbelievable amount of data that you can gather. So one question that you may now have at this point, and we're going to talk about in quite a bit coming up in this, in future lectures or future sections and videos of this lecture. How do we figure out an appropriate f sub s, n, and t to capture my signal? If we're doing an experiment, a new experiment, looking at new data, how do I figure out these values? What values are appropriate? Well, that is a great question, and it leads us to kind of the key concepts, two critical concepts that we're going to be talking about in discrete Fourier transforms. First being signal aliasing, and the next being spectral leakage. And in the meantime, we're going to figure out also how to do DFT and calculate our harmonic coefficients, A sub n and B sub n, and how do we get our frequency spectrum. So more of that coming soon. Thanks, and I'll see you all in the next video. Have a good day. All right, bye.